If we want to interpret a 2's complement represented number, we can determine its value using techniques that we learned when we discussed positional notations. Given a specific number of bits, the rightmost bit has a weight of 1. The second rightmost bit has a weight of 2, and so forth. The most significant bit has the magnitude that we might expect, but it has negative weight. Consider this 4-bit number. In unsigned binary, this number is 11. But in 2's complement representation, this number is negative 8 plus 2 plus 1, or negative 5. One last important thing that you need to remember is that just like any other representation in a computer, 2's complement requires you to have a fixed, defined width to the number to be able to interpret it correctly. The nice thing, and the reason why we use 2's complement representation, is that we can add negative and positive numbers with the same algorithm that we use for unsigned binary numbers. Let's add the 4-bit 2's complement representations of positive 5 and negative 5. Ideally, we should find that the normal binary addition algorithm will yield an answer of 0. So 1 plus 1 is 0, and we carry the 1. 1 plus 1 is 0, and we carry another 1, and so forth. We cannot store this final carryout of 1, so this computer will store the 4-bit number as 0. Hey, it works! Now that we know that we can add positive and negative numbers, we can use this new tool to subtract two 2's complement represented numbers. As you know, when we subtract one number from another, we are actually adding a number that has the same magnitude but opposite sign of the number that we're subtracting. So, if I want to subtract 3 from 6, I really want to add negative 3 to 6. So how do I convert a positive number into a negative number? Fortunately, 2's complement representation has a convenient algorithm for changing positive numbers into negative numbers and vice versa. Simply, you complement all the bits, change 1's to 0's and 0's to 1, and then add 1. Finally, because 2's complement representation is constrained by the fixed number of bits used by the computer, we must make sure that the architecture can perform the calculations that we want to perform. Generally, an n-bit 2's complement represented number encodes a range of negative and positive numbers. For 4-bit 2's complement representation, the representation encodes 16 numbers from negative 8 to 7. Let's see what happens when we add 5 plus 5. Notice how the most significant bit in the 4-bit number is 1. By adding these two positive numbers together, the magnitude of the sum, 10, exceeds the limit of the representation, which was 7, and produce an error. Similarly, if we add negative 5 plus negative 5, the magnitude of the sum will exceed the limits of the representation and produce an error. This problem is called overflow. More generally, overflow is an error where the magnitude of the sum of an addition operation, or any other operation, is greater than what can be represented by the representation. As we just saw, when the magnitude of an addition operation in 2's complement representation is too great, the positive number will be wrongfully interpreted as a negative number, and vice versa. Similarly, with unsigned binary addition, we can have overflow when the magnitude of the addition exceeds the representation limits. If we add 10 plus 12 in 4-bit unsigned binary representation, the sum is 22, which is greater than the representation limit of 15. Consequently, the overflow causes the computer to display the sum as 6 rather than 22. One last note. The carryout of the most significant bits in an addition operation is called the carryout bit. It is not an overflow bit. They are two different words, and I just want to make sure I emphasize that because that is a point of confusion for so many students. Carryout is different from overflow. Please try to remember that.